Hi, this is Xiaowen from Lehigh University. In this video, I'm going to present our paper, Weakly-supervised Object Representation Learning for Few-Shot Semantic Segmentation. Semantic segmentation is a task of assigning a class label to each pixel in the image. It is one of the fundamental tasks in computer vision. Although the state-of-the-art deep learning-based segmentation models are very powerful, training such segmentation models requires large amount of pixel-wise annotated images, which is costly to obtain. Also, once the training is done, the model is limited to segment those predefined classes in training sets. To conquer these challenges, we tackle the problem of few-shot semantic segmentation. The goal of few-shot segmentation is to perform segmentation tasks on unseen object categories merely based on one or a few support examples. The key to solving this problem lies in effectively utilizing object information from the support examples and use such information to find the target object in the query image. While existing methods typically generate object-level representation by averaging foreground features in the support image, we found that such object representations are typically noisy and less distinguishable. To solve this problem, we present a new few-shot segmentation framework by incorporating a novel object representation generator module with a modified encoder-decoder architecture. The proposed ORG module is designed to train in a weakly supervised fashion and learns to aggregate local features to produce better object representation for this task. The proposed architecture consists of an attention branch and a segmentation branch. Given the support example and a query image as inputs, the attention branch first utilizes the proposed ORG module to generate an object-level representation from the support example, and then use this support object representation to produce an attention map on the query image via the comparison module. The attention map can be seen as a course prediction and will be fed into the segmentation branch to provide guidance information and produce the final result. One of the key components in our framework is the ORG module. It consists of several convolution blocks that learns to produce object representations and a parallel foreground average pooling branch that serve as a regularization term. Although the architecture of the ORG module seems straightforward, the key problem is that how can we train this module to produce better object representation? As a human being, we don't know what kind of object representation is better for this machine learning model, so we cannot directly provide supervision to the outputs of the ORG module. To solve this problem, we design a training scheme that can indirectly optimize the ORG module. The basic idea is that we can generate the object representation from the support example first, and then use it to find the source object in the support image itself using the same comparison module and the segmentation branch. We can then use the support mask itself to supervise these two outputs. Intuitively, this learning process forces the ORG module to improve the quality of the generated object representations such that it can better segment the source object itself in the original support image. We refer to it as the Weakly-supervised learning scheme. We evaluate our method on two public benchmarks for few-shot segmentations. Both Pascal 5i and Coco 20i are constructed in the form of four-fold cross-validation, and there's no overlap of the object categories between training set and the testing set. These two tables shows the quantitative results on two benchmarks. We can see that our approach consistently achieves better performance compared to all existing methods in terms of the mean over four-fold cross-validation, which demonstrate the effectiveness of our approach. It is worth mentioning that our results without multi-scale testing are even better than two existing methods with multi-scale testing, and our results using smaller input resolution are even better than the existing approach using higher input resolution. This figure shows the qualitative results of our approach compared to two existing methods. We can see that our results are also visually more accurate and more stable. We have also provided more qualitative results on challenging scenarios, including one-to-many matching, many-to-one matching, object size variation, viewing angle variations, as well as some interesting failure cases. Please feel free to download a PDF version of the slides and take a look at these interesting results. Thank you for your interest in our paper, and I hope you enjoy this video.